Step 5.5, data structure analysis. Now we want to look at segment level stability analysis. We can do this either within solutions or across solutions. So first we'll look at segment level stability within solutions. We are using package flex cluster for this. We're setting random seed and we're generating artificial data, which is a 3-cluster structure and contains 500 observations, and it's 2-dimensional data. We are running step CC cluster, so we're running the k-means algorithm on that dataset with number of segments from 3 to 8. So we're running all solutions, all market segmentation solutions for 3, 4, 5, 6, 7, and 8 number of segments. And we're running the k-means algorithm with 10 random initializations each. So we can see the progress of the algorithm. Here the number of segments, here the repetitions for the random initializations. And then we can relabel them, which means here we have a sequence of solutions and we are relabeling it so that the numbers align over the sequence. We see this function relabel internally use functionality from package clue. So package clue needs to be installed that we are able to use the relabel function. And what we're doing here is we're extracting the 3-segment solution and we're extracting the 6-segment solution, because first, if we're looking at stability within solutions, we want to look more carefully at what the stability for the 3-segment solution looks like and what this segment level stability for the 6-segment solution looks like. To get an idea of what it could look like, we'll investigate what the solutions look like first. We're splitting the plotting window into a 1x2 matrix, and we plot the resulting segmentation solution with the dataset, and that's the title we want to specify, and this creates a neighborhood graph. So the neighborhood graph gives us the centroids of our segmentation solution. The edges indicate how close they are, and we have the data points themselves, and there would also be the convex hulls. Hard to see in that plot here, but we see the 3-segment solution perfectly groups the observations into the true underlying distinct segments, whereas the 6-segment solution has one segment, the number 6, which is identical to a true segment, whereas the other 2 segments, they're split into smaller bits. So segment 1 is split into 3 small segments and segment 2 is split into 2 other segments. So if we run segment level stability on it, here we would assume all of them should be stable because all of them represent natural segments. In a 6-segment solution, we would expect only segment 6 to be stable and the others to be unstable. So if we want to do this, we run now the segment level stability within flexclust function, SLSW flexclust function, on the dataset, and we also put in our fitted object, because what we need to do is we need to generate bootstrap samples, and then we compare the solution on the bootstrap sample to the solution we found on our original dataset. The easiest to inspect the result is to plot it, and here we use the layout function to split our graphic window such that we have more space for the 6-segment solution than for the 3-segment solution. This is what we are specifying here with the width. So we want to have a 1 row, 2 columns, plot 1 and 2. We want to have aligned like that, and then we plot the segment level stability within plot for the 3-segment solution and for the 6-segment solution. That's limits for y-axis, label for x-axis, label for y-axis, and the title. I've gone down, we plot, and we see here we have our parallel box plot, a box plot for each Jar-Coheed coefficient distribution for number of segment 1, segment 2, and 3. All of them are stable in the 3-segment solution. The 6-segment solution, only segment 6 is stable and all others are unstable. And we can do the same kind of analysis now on real dataset using the vacation motifs dataset. We again run k-means clustering, but with a different algorithm for finding the optimal partition. We're using the neural guess method, but we use number of segments from 3 to 8 all of these solutions are investigated with 20 random initializations on that dataset. We are saving the data with the object, and where both equals false means we don't want to have progress information plotted while the algorithm is running. So here we don't see any progress information compared to the progress here. Alright, so once step CC class finished, we have the returned object. We can relabel again our sequence of partitions, and we can extract the 6-segment solution. Then we can run function SLSW flex clust on that 6-segment solution using the dataset, and we want to use again the method neural guess for finding the partition using the CC clust function. So we need to run that algorithm, and we also need to wait for this function now to finish. And once we have the segment level stability indices calculated, we can again plot them with changing the axis label, the y-axis label, and the limits of the y-axis to see segment 3 is unstable, segment 1, 5, and 6 are the most stable.